So, how do neural networks work and how can you manipulate and attack them? We will show some examples to make the theoretical concepts tangible. And also, there are defense strategies that have been developed. Jate, who also likes mathematics, will guide you through this talk. Jate, welcome and thank you. Good morning. Yeah, I'll give you an introduction to hacking neural networks. I've worked for a long time on neural networks, and lately I've been finding it interesting to look at the hacking perspective. How can you manipulate those things and what can you do with them that you shouldn't do? This is what I want to present in this talk. And I want to present it to you because I find it very interesting and wanted to share with you. But as a disclaimer, this is nothing super new. I'm not going to present any new findings. About myself, I've studied mathematics, and this is why I have a mathematical view on this machine learning thing. And it's kind of a hate-love. I love maths. It gives me structure. It helps me to understand things. And this is exactly what is missing in machine learning. We will see that shortly. There are mathematical concepts in machine learning, but as soon as it comes to the application, it's basically trial and error. So for me, I like to look at it and then I get too much and then I like to look into it again. So as an overview, what are we going to do today? First, I would like to get us all to a common base of knowledge, look at the application, and then the attacks which I listed here. I divided it into the perspectives of the pure user who interacts with the model and does nothing else. Then we have read access to the model, and then we try to do something, manipulate the model and see where we can get. And then the last step, we even have write access, and we can do anything we want to do to the model. And in the end, I will give you an overview of how to defend against such attacks. So let's start with the overview of neural networks. Today, we have two applications of neural networks. One is specialized AI. Specialized AI is trained to solve a single problem and can only solve this one problem. And this problem specialized AI can solve can be divided into two classes. One is classification, which is the upper example, to know whether there's a dog or a muffin on the picture, which is actually pretty difficult for a neural network. And the second class of problems is the so-called regression. Regression means you have data on a time interval, for example, and you want to see, look, for this point in time, I don't have a measurement value. What will the value be? That will be an interpolation. So the model is trying to see what value will be there. And on the other hand, which we saw last year, we have generative AI. So this is an AI that is capable of creating something new, something that hasn't been there before. And this is done using specific data. We've seen ChatGPT that is specialized on language, for example, or image AIs. And what is special about generative AI is that good and bad is hard to define. I want to have a picture which wasn't there before, and I don't know at the end of the day whether the picture that I generate is good or bad. And it's the same with language. You want for example, you want a summary of a text. The result could be satisfying for me as a human, but still could not be perfect. So generative AI is you can manipulate it. Language is unclear, and what the result depends on my judgment of whether it's good or bad. So between those two classes, we have a certain discrepancy. In the following, I will refer mostly to specialized AI. And the attacks that I will present can also be used for generative AI. So I'll look at the first attack, that is prompt injection. I wanted to keep it short because I don't find this very interesting from a technical perspective. I've brought you an example. It's a game where you play against a chatbot. The chatbot has a secret which it's not supposed to tell you, and now you as a human have to generate input in order to manipulate the chatbot to give away their secret. And I find the solution very fascinating, because it's very short. YTL is a rule from the internet. It's part of the training data, because at the end there's TLDR, too long don't read, and under that you have a summary with all the contents. And so with a rule that is part of the language that isn't explicit, I can trick the whole algorithm. So that is the point. Language is unclear. Humans sometimes have trouble interpreting sentences, because one sentence can be interpreted in many ways depending on the situation. And especially this translates well to the generative models. So there's a lot of room to maneuver and manipulate these algorithms. So I'll leave this here because I don't find it too interesting from a technical perspective. So let's look at what is learning. In the case of neural networks, learning means optimization. Optimization is a mathematical concept, a nice mathematical concept in my personal opinion. But to translate this to machine learning, I need a large amount of data, and this data needs to be labeled well. Labeling means that you can associate data with one another. For example, the dog in the mapping example, all images with the dog somehow have to contain a dog, so that the model can learn, okay, this is what a dog looks like. So this is work that humans have to do. To do the training, there is some freedom. You can choose your architecture, so how neurons interact with each other, but that's free to the developer to decide. Then I have to choose a loss function. The loss function defines what is good and what is bad, and it depends on which problem I want to solve. And then I choose an optimization algorithm. There's many different algorithms, and it's not clear which algorithm is right in which situation, so you kind of have to do the guesswork and find out. Then I start doing my mathematical optimization, which is an iterative process. The architecture defines the parameters, and I adjust the parameters and try to get to a point where the error is minimized, so that my training data is well classified. And I want to reach another goal, which is generalization. This generalization means that my model isn't only applicable to the training data, but to real-world data as well. So what I hope is that my training data have a good image of the world, a good picture of the world, but that is a hope, and I can't say whether it's correct or not. So let's look at what a neural network basically is. A neural network, on the left, you have a flow chart where different things are connected to each other and interact with each other in some way. But you can put that very nicely in a mathematical formula. Then I have an input, that is the blue, the x's. Then I've got the weights that are defined in the architecture. This is what is adjusted. And in the end, I've got the red things. This is something I can also adjust in my optimization algorithm. But in the end, I modify using weights. And this is what the flow chart shows. And this is what I throw into a nonlinear function. And I do that again and again. So this is basically what a neural network is. So enough said about neural networks. Let's get to the attacks. So let's assume we're a user. We can interact with the model. What can we do? The first thing we can do is try and steal the model by mimicking the architecture. For example, an image classificator that gives me results like this is a dog, this is a cat. And the point is, I only need the training data. I only need the data that code the rules, and I don't need more information because the architecture I can choose. Well, different architectures give similar results or good enough results. And this means that I can automate creating these or generating these data. I've showed you an example, two classes that we want to divide. The second data set was created, well, I just created one neural network, gave it the input data, asked it to classify them, and you don't see any difference. And then I take a different model, a different architecture, and train it to the stolen data set. And this is what you can see on the very left, or on the very right from your perspective. The functionality can be mimicked independently from the architecture. So this is the first attack I can do. Next, I will go to brute forcing, and to show brute forcing, I will use another example. Well, I just forgot one thing. The model stealing, we could say, well, that's a very academic approach, but it is happening in real world. For example, just in December, the account from Violence was banned by OpenAI because they said they're taking our data to make their own models. They're using ChatGPT to train their own language AI, and this is this is actually happening. Data are stolen, are put into different architectures, and are reproduced. Now let's really get to brute forcing. I will use another example to show that. An authentication. I've got a website where you have to upload a secret. This is something like a password. In this case, it's an image. So I have to upload an image, and hopefully I'll get access to what I want to have access to. Authentication with neural networks is a really bad idea. You should not do that. Let me stress that at this point. So this is how it should work normally. The neural network trains a classification of handwritten digits that are put into images of 28 by 28 pixels. And if you upload a 0, you don't get access. And if you upload a 4, you get access. So the common secret is the 4. And this should mean I always should get access to those things whenever I upload a for. But because I said it's an authentication, we can do the same attack as for any authentication. We can brute force. So we can just upload any image. So at this point, I wanted to show you where's the neural network in the code. How does it work? I upload an image, and I've got image pre-processing, and at some point, the trained neural network is loaded. And at the point I marked with the 2, I have the classification of the image that was uploaded. And the result is not 4, but it's a 10-dimensional vector. And we will see at which point is the maximum. And then that's translated back into the number. And in the last step, I have a condition that says, is that a 4 or is it something else? Now really. And let's get to the brute forcing. I can just create random images because any image that is put into the neural network is classified in these 10 dimensions. So the neural network tries to discern whether my image contains a certain pattern that is contained in the training data, and that has nothing to do with the fact that as a human I say it's a 4 and the neural network also says it's a 4. I can just generate random images, and at some point I will find an image that will grant me access, even though for me as a human there's not a 4 visible in the image. And that is what I found pretty fascinating, because I understand that the understanding of these images does not conform to my understanding. So this type of learning has nothing to do with what we define as learning as humans. And if you go one step further and say, okay, now we've interacted as a user, but then we've found the model. For example, we right-click our authentication page, look at the source code, and then there's a GitHub link, and boom, we found the model. So now we have access to the model, can look at it, can look at its structure, and this information usually also gives us information about the optimization, which parameters were chosen. And what I can actually do is I can take an image generator and train an image generator by saying, okay, here's my actual pre-trained networks. I'll fix that. I'll do nothing to that, but I'll add another layer, and one layer is enough before that. And I adapt that layer in a way that the image generator generates something that looks for the other network like what would look like a 4. So with the brute forcing, I have to do a lot of trial and error. But in this case, because I have read access, I can look at the whole layer, and I see how the 10-dimensional vector is created. So there's 10 classes. So I can just create an image for class 0, class 1, class 2, class 3, and so on. And in the end, I've got 10 images which I need to upload, and in the end, I can manipulate the neural network with this trick and generate an image that the neural network will accept.
And that's not enough. I can also take the picture and change it slightly. These pictures on the left-hand side, they look slightly different than on the right-hand side. I just put some noise on the pictures and looked, when do I start not having access anymore? And so there's still the possibility that the neural network classifies these as A4. And then I asked myself, what happens if I take a 4 and then put noise on the 4? Can I destroy the pattern so that it doesn't classify as a 4? And the same happens. This is possible as well. So on one hand, I have many pictures that for me as a human don't look like A4, don't look like the secret, but they give me access nonetheless. So I can trick the neural networks. On the other hand, I have just as many 4s that as a human I recognize as a 4, but the neural network doesn't. So we learned just the same as before. Learning doesn't really have anything, or it doesn't. It's not comprehension, and it doesn't have anything to do with what I do as a human. So we'll take another step here. Now we have write access. So we can actually modify the model, and we can start to play with the parameters, and we can change the parameters. So one of the most interesting things is the last layer, because the last layer takes the decision. Everything before it is nice and well, but the last layer is the one with the 10-dimensional vector that gives the result. And as I've seen before, I take a look at what is the largest number in this vector, and that's what the neural network sees. The numbers are all comparatively small and close to each other, even after learning. And so now, when I have write access, I don't really need new training. I can manipulate the neural network to do what I want. On the left-hand side, you see the neural network, how it's built. And then I only take the very last part, that part that is labeled dense 2 here, or the bias of dense 2. That's the part I will take. I've shown this on the right-hand side, and I just put on that part which I want to be classified as positive, I put a very large number, and that's one way to modify the neural network. And everything changes, and I mean like everything. It doesn't matter what you put in, whether it's noise, everything will give me back A4. So that was quite impressive. I thought, just change one number and all of a sudden the complete functionality of the network is destroyed. Right, so let's go back to the example where I have write access, but maybe not onto the neural network, but only on the data. So what I can do here is I can modify the data. I mean, the data they codify the rules, of what needs to be recognized on other pictures. When I look at that relationship between input and label, and when if I can destroy that relationship, like if I change the labels, or I generate user access and generate results that are quite similar, then I can change the correlation between input and output, because the network can't learn anymore what the rules are. The rules aren't clear anymore. I am showing this on the example of the classification. On the second plot, you can see that the blue and the red dots are quite overlapping. So I've changed the labels of the data points, and on the other side I've trained the neural networks, and you can see it looks quite different. It still has the same core functionality, but there's not much relationship to what the original network did. And if I have access to the training data, then into the training data I can put a picture, like classification or authentication. I can put something in where I put my label in that I want to get out, like a triangle, for example. And I put that into the training data, then the user doesn't know that that picture actually exists and is classified accordingly. So the training data are something that you want to protect. And like I said, the data contains the rules that need to be learned, and if I can manipulate that, then I can completely destroy the neural network. So that was all the attacks that I wanted to show.
So regarding the defenses against these attacks, what can I do to prevent them? For example, model stealing, I can apply something like rate limiting, but we all know this is not really the best way of it can be prevented as well. Regarding brute forcing, rate limiting can also be applied to prevent that, but using authentication this way is a bad idea. So the brute forcing can be used on the side of the user, the trainer, so that to get a better understanding what the neural network is actually doing by generating out of sample data. The heaps of pixels, they are not present in the training data. So I can use them and see what happens and try to see the classification and understand better how the classification works. Regarding adversarial attacks, this is basically about protecting the neural network. I need to understand this is something sensitive. I need to store it in an encrypted manner. I need to guard it, and I need to make sure that I don't lose it. The same then also applies to a LastLayer attack, of course. I don't want anyone to modify the neural network and modify that in any way. So it's highly sensitive data, I need to protect it. And adversarial attacks can also be used to gather information about the actual training data. So if I refine the image generator, I will get to the point that information which is contained in the training data becomes accessible. What I've shown here, I've done this in a very rudimentary manner. This takes a few minutes, and then I get an image which allows me to access the system. This can be refined, of course. I can try to extract more information from it. Regarding data poisoning, we're at a point, so the training data are also sensitive. I need to make sure they don't get lost. If I lose them, I lose the rules that I want to learn. And for data poisoning, I see it as something like a supply chain. So we have a lot of software all around it, which is created for training the neural networks. And this software has leaks, can be attacked, and I need to make sure that this software is given only to the people that actually use it. I need to make sure that if there are any potential attacks, that they can be prevented by patching the software. So we all know about this, and hopefully we're already taking care of all of these things.
Thank you for your attention, and I'm open for questions. For questions, please come up to the microphones. First question from the internet. Is there anything? There's no questions from the internet, but a big thank you for this interesting talk. Thank you very much. Mic number 1. So I don't really know a lot of neural networks, but what about the biases and the thresholds? Can thresholds not be modified such that under a certain value the result is unclear and you have to retry? Well, of course you could do that, but that would mean that you need to play with the threshold. So, if we take a look at the classification, the red and the blue dots, the neural network will output something that lies between 0 and 1. And if you're saying everything beneath 0.5 is 0 and the other one is 1, you effectively already have a threshold which you can play around with, but I think if I understand the question correctly, then you would like to have some measure of likelihood that the network is correct. If I do that, then I have to define this likelihood, which is just another prediction of yet another neural network. How much trust can I put into that? So the other point is that these pixel heaps being classified as a 4, you can get a very high likelihood of this being a 4. Well, the network says so anyways, but it still isn't.
Okay, mic 3, please. So, in your example with the adversarial network, where images react that have nothing to do with the actual image, what would you say, how would you counter the argument that people are saying, well, this is just because the network is very simple. If you could have a more complex network, they would see more like a human and those attacks wouldn't be possible. Well, I think it's a cat and mouse play. I think it will always be possible. Every image is classified somehow. So even a heap of pixels can result in a number. And I would have to reformulate the problem. So look, here's a heap of pixels that classified as a pixel. So I would have to have 11 classes, and I would have to be able to discern, maybe in a pre-processing, whether an image actually contains a number. I don't think that by just changing the architecture you can prevent this attack, because you can also just scale up the complexity of your adversarial network and train it to learn those patterns. Thank you.
Well, thank you very much for this talk. So my question is about training data and poisoning. So assume that if I was the largest internet concern and had a lot of training data that I have access to, is there any rule of how high the percentage of bad data has to be for it to make an impact? And if I wanted to make that impact, is it better to use training data that are subtly false, or should they rather be completely off? So I just found 2 papers that try to answer this question on a threshold. It's very low. It's like below a percent. Even below a percent, you can do something. The question is, what do you want to achieve? Would you like a backdoor, or would you maybe like to destroy the entire structure? The other question is, what's your application? Like, if you take an iris scanner as an example and you put a cat picture in, that's easy to recognize. But if I put an orange iris in there, if that is classified, that's quite inobtrusive. One point is that So to train the nets that works today, you need a lot of data. So for ChatGPT, for example, that used 5 terabytes of text data. No human could look through that, and that should be easy to smuggle something in that, well, if it's completely off, you might be able to recognize through statistical methods, but if it's close to the data, then it's much harder to recognize that. My suggestion would be to pick something that is close and don't be off by too much, and that means you can hide in the haystack.
Next question, mic 3, please. Hi. Thank you for your presentation. I would like to pick up what the previous speaker said. The problem is we need training data, and the faked training data need to be injected somehow, so we need access. So either I can use and fake data sets that are on the internet, so that goes into the direction of what you said about ChatGPT, that I can do prompt engineering. I discuss with the model, and if I tell it, show me an apple 300 times, and then tell him, no, bro, that was a pear, maybe you need to change something. So how likely is it that we can use those attack vectors on ChatGPT, for example? Well, because we're interacting with language, and language is always imprecise, there's always room to maneuver. It's also a cat-and-mouse play, especially with the adversarial attacks. There's hundreds of papers that are saying, look at this adversarial method, look, we've got this method to prevent it, and then the next attack evolves, and so on and so on. So especially with language model, there's a lot to gain, because rules of language are very flexible, and you can play with them and see where you can get. So I think it's very likely that this problem will never be able to be solved. Well, and yeah, it can result in getting access to training data that can be manipulated, whereas on the other side, the images have been created internally and labeled internally where I don't have access. Well, yeah, if you don't have access, you can only guess. You can try and brute force. And if it's closed source, it's difficult to attack. So that's definitely correct. But all of the training data sets are public, so in this paper, Hacking Neural Networks, a short introduction, they have the scenario that I'll train a data set that looks, or I label it as a well-known data set and introduce my vector. I try and push my data set, and it will be accepted by the community, and then I've got my training data set in there. So with enough creativity, I can inject a vector into training data, and I think no company can actually verify this amount of data sets and create it yourself.
Okay, Mikrofon Nummer 1, bitte.
Thank you for the talk. I have a short question into the direction of defending against brute force attacks. So every input will lead to some output, to some class of output. Is there a point in defining a catch-all class? I think you talked about it. Something that triggers if it's neither 0 or nor 9, and it triggers with a high likelihood of not being a number of all. Are there any approaches this way? Or are there training data that have lots of non-number pictures? Well, I think the best approach would be two-pronged. So first, staying with images, image processing, do an object detection on the image, and that means you will sort away a part of that pixel heap. And the second case is or the second prong is to define the catch-all class. And you don't need a whole lot of catch-all that will lead to an unbalanced data set that makes learning difficult. So I think catch-all should maybe be as large as the rest of the classes to make it more balanced. That would be a training data set with 11 classes. And I think that would get you quite far. Thank you very much.
So one last question, Mike 2. Just a short question on understanding on the first method. You explained it very briefly. I think slide 9, I'll just create stolen data and make a similar model. Could you elaborate on how to steal the data? Well, I assume that I can only interact with the model as a user, so I enter and I get a model back. Just like ChatGPT, I enter my question and I get an answer. And this is the data I can use to train a different model. For an application like a chatbot, that's a lot of data, but maybe I already have data. For example, I broke down Wikipedia and I want to enrich my data set with the questions and answers or question-answer pairs. And I can use the neural network because I can interact with it to create data and use in my own model. So this was my thoughts. So I have access to the functionality and I use the functionality to extract data from the model without knowing exactly what is happening in the black box. Okay, thank you. So I can see that there's several questions left, and I'm sure that Jate will be at your disposition outside the room. So thank you for now.